Good evening, everyone. Today, I am excited to present on a fundamental concept that plays a crucial role in modern day technology, the Fourier transform. Whether we are dealing with telecommunications, audio processing, or even the images we see on our devices, the Fourier transform is the mathematical backbone enabling these advancements. In this presentation, I will walk you through the basics of Fourier transform and explore its wide-ranging applications in signal processing. My name is Ajaz Ahmed and I am presenting these as a part of our course on signals and systems. Before diving into the applications of the Fourier transform, let's first understand what it actually is. Simply put, the Fourier transform is a mathematical tool that allows us to break down complex signals into simpler components, specifically into their frequency components. This transformation gives us a new way of analyzing signals by looking at them in the frequency domain rather than just the time domain. Why is this important? Well, it's everywhere in the technology we use today. Whether it's your phone compressing an audio file, a video streaming service ensuring high quality images, or your internet provider transmitting data. The Fourier transform is working behind the scenes to make all these systems efficient and reliable. Its ability to manipulate and analyze signals is indispensable in telecommunication, audio processing, and image processing. Now, let's take a quick look at the origins and mathematical foundation of the Fourier transform. This concept dates back to the early 19th century, where French mathematician Jean-Baptiste Fourier introduced it while studying heat transform. His revolutionary idea was that any complex signal could be represented as as a sum of simple sine and cosine waves, each having a specific frequency. This brings us to the distinction between the time domain and the frequency domain. In the time domain, we observe how a signal changes over time, but sometimes this doesn't give us the full picture. The Fourier transform converts this time domain into the frequency domain, where we can see the individual frequencies that make up the signal. This shift in perspective makes it easier to analyze and process the signal. Now that we have a basic understanding of the Fourier transform, let's dive into some of its key concepts. First, we have the Fourier series, which is used to represent periodic signals. However, for non-periodic signals, we use the Fourier transform, which extends the idea of Fourier series to handle a continuous range of frequencies. There are two main types of Fourier transforms that are commonly used. The continuous Fourier transform, which works for continuous signals like analog, audio, or temperature variations. And the second one, the discrete Fourier transform, which is essential for digital signals such as those used in computer based systems. The discrete Fourier transform helps us to analyze sample data points, and it's made much faster by the fast Fourier transform algorithm, which drastically reduces the computational complexity. Lastly, the inverse Fourier transform allows us to go back from the frequency domain to the time domain, ensuring that we can reconstruct the original signal from its frequency components. This two-way transformation is what makes the Fourier transform so powerful in signal processing. One of the most powerful applications of Fourier transform is in signal decomposition. This means that a complex signal, which may seem difficult to understand in its raw form, can be broken down into simpler sine and cosine waves. These simpler components represent different frequencies that make up the original signal. This process is particularly valuable in audio processing. For example, when we want to reduce noise in a recording, we can transform the audio signal into the frequency domain. Once there, it becomes easier to isolate and remove unwanted frequencies, such as background noise, while keeping the important parts of the audio intact. Similarly, in audio compression, like MP3 encoding, the Fourier transform helps by eliminating inaudible frequencies, making the file size smaller without noticeable loss in quality. So, by breaking a signal into its frequency components, we gain the ability to edit, enhance, and optimize audio content with precision. Beyond audio, the Fourier transform plays a crucial role in image processing as well. Just as it decomposes sound into frequency components, it can also transform images from the spatial domain into the frequency domain. This allows us to analyze the frequency content of the images, which is especially useful for various filtering techniques. One of the key application is image filtering. For example, low pass filters removes high frequency noise, which results in a smoother, less detailed image. This can be useful when we want to reduce noise while maintaining the overall structure. High pass filters, on other hand, enhance high frequency components like edges, help to sharpen details, or highlight fine features in an image. Moreover, the Fourier transform helps in noise reduction for images, just as it does in audio. By selective filtering out unwanted frequencies, we can clean up an image while preserving the important details. This technique is widely used in medical imaging, photography, and even video streaming services to improve visual quality. The Fourier transform is a key enabler in communication systems, where it plays a central role in transmitting data efficiently. One of its primary application is in modulation and demodulation. To send data over communication channels, we need to modulate a signal by encoding information onto a carrier wave, which can then be transmitted over a variety of media such as radio waves or optical fibers. At the receiving end, we use the Fourier transform to demodulate and extract the original information from the carrier signal. Another important application is frequency division multiplexing, FDM. FDM allows multiple signals to be transmitted simultaneously over the same communication channel by assigning different frequency bands to each signal. This is made possible by the Fourier transform, which helps us to break down and isolate these signals at the receiver. For example, in wireless communication, different frequency band can carry data, voice, or video simultaneously, optimizing bandwidth usage and improving the efficiency of the data transmission. These applications highlight how the Fourier transform is crucial for managing the vast amount of the data we transmit daily in modern communication systems. To wrap things up, let's quickly recap the key points we have covered. The Fourier transform is a powerful mathematical tool that allows us to convert signals between the time domain and the frequency domain. This transformation provides deep insights into the structure of signals, enabling us to analyze, process, and optimize them. We have seen how the Fourier transform is essential in audio processing, helping reduce noise and compress data, and in image processing, where it enhances image quality and reduces noise. We also discussed is its crucial role in communication system, from modulation to frequency division multiplexing, which allows for more efficient data transmission. The Fourier transform's significance in modern technology cannot be overstated. It's the foundation for many of the systems we rely on every day, from streaming audio and video to reliable data transmission over the internet. Looking ahead, the Fourier transform will continue to evolve with the advancement in the signal processing, especially in areas like artificial intelligence and machine learning, where real time processing and enhanced algorithms will push the boundaries of what's possible. As technology grows, so too will the application of Fourier transform in shaping our digital world. Thank you very much for your time and attention. I hope this presentation has given you a clear understanding of the Fourier transform and its application in signal processing. Now, I would like to open the floor for any questions you may have. I will be happy to dive deeper into any of the topics we discussed today or clarify any concepts. If you have any further questions after the presentation or would like to discuss any aspect in more detail, please don't hesitate to reach out me via email. Thank you once again.